Hi, my name is Chris Schulte, and we're talking about lab number 3, the topic of circuits. The purpose of the lab was to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel. The goal of the lab was to enhance understanding of circuits with resistors, as well as using multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. Some fundamental physics principles models used in the lab include Ohm's law, which states that the electric current through a connector between 2 points is directly proportional to the voltage across the 2 points, or delta V res equals IR. The loop rule, also known as conservation of energy, which states that the sum of all electrical potential differences around a loop is 0. The node rule, which states that the current flowing into a junction must be equal to the current flowing out of it, or conservation of charge. We also use the principle of capacitance, which states that the capability of a material device to store electric charge is equivalent to Q divided by V. Overview of results. The system in this lab was a circuit calculated by the software, and there are no surroundings. Results. For all circuits and scenarios created, the principles of conservation of charge, conservation of energy, Ohm's law, and capacitance were upheld by the computer model. Predictions created from these principles consistently align with the generic computational outputs. The experimental time constant and the true time constant are roughly equivalent, or 5.9 seconds is roughly equivalent to 6 seconds. Experiment and data analysis. The initial conditions can be referenced using the visualization at the left of the screen. The predicted value for currents I1 and I2 measured by the ammeters were 0.0204 amps, which was calculated using the equation EMF minus IR total equals 0. Both ammeters read 0.02 amps, which aligned with the prediction made above. When the connection to the ammeter was reversed or inserted backwards, it read negative 0.02 amps, which is the same magnitude but opposite in sign. After replacing one of the ammeters with a voltmeter, the ammeter reading was 0 amps and the voltmeter reading was negative 3 volts. The ammeter reading is 0 because it is open circuit, while the volt reading is negative 3 volts due to the direction of the current and the placement of the probes. The black probe is at a point of peak potential difference due to the batteries. Removing the voltmeter from the circuit, closing the circuit with the wire, using the voltmeter to measure the potential difference for each part around the circuit path, we see that AB is measured to be 3 volts, CD was negative 0.959 volts, and EF was negative 2.041 volts, while other segments were 0 volts. These were calculated using equations EMF minus I times the 47 ohm resistor minus I times the 100 ohm resistor equals 0, and the fact that BC, DE, FG, GH, and HA were all equivalent to 0. The current I was measured to be 0.02 amps, and the round-trip potential difference should add up to 0 as per the loop rule, and the results above confirm this. When attaching the voltmeter, the ammeter reading does not change because it has no net effect on potential difference or the current of the circuit. Delta V after connecting the voltmeter across the 100 ohm resistor was negative 2.041. The current is increased because the resistance decreases. Both ammeters are included in the loop, including the 100 ohm resistor. We also see the graph of potential versus position around the circuit, where the electric field, which is the negative gradient of the potential, where the slope is steeper, the electric field is larger, or in this case, the slope is steeper and the 100 ohm resistor compared to the 47 ohm resistor. Some values determined for the 47 ohm resistor, the resistance was 47 ohms, the resistance for the 100 ohm resistor was 100 ohms, whereas our wire was 0 and our ammeter was also 0 ohms. These were calculated using delta V equals IR. For the RC circuit, after connecting the batteries to the light bulb and capacitor in a series of light bulbs and slowly as time progresses, when the battery is disconnected, the capacitor discharges instantaneously, lighting up the bulb, which then begins to dim over time. After connecting the battery to the capacitor and light bulb, the current in the circuit decreased. After removing the battery from the circuit, the current in the circuit decreased over time. The 10 ohm bulb charge time is 9.7 seconds, while the 20 ohm bulb charge time is 19.72 seconds, and the discharge time was 8.89 seconds and 15.48 seconds respectively. Here we see that the computed value agreed with the time constant value of the circuit. The RC is equivalent to the time where the voltage is approximately 1 divided by E of its original value. The time constant is equal to 30 ohms times 0.2 farads, which equals 6. Here we see the linearized data from the table on the right. Conclusions. Some ideas and takeaways include the relationship between Ohm's law, loop rule, node rule, capacitance, and linearization, and the behavior of a circuit. Assumptions and error analysis. We assumed steady-state equilibrium in circuits without a capacitor, as well as resistance is negligible in ammeters and wires. We said that the equation EMF equals V cap plus V resistors, but since this experiment was done computationally, there is likely minimal to no error in this lab. The only potential source of error is human error when timing charge and discharge times. If the lab was done in real life and actual ammeters used to simulate ammeter, the ammeter would have a small amount of resistance, which would have decreased the total current of the circuit. Also, if it was done in real life and used a real battery to charge a real capacitor with no resistor in the circuit, our ideal model would predict that the capacitor would be instantly charged when connected to the battery without resistance. However, in an unideal system, there would be a delay and it would also have to face resistance from the wire, even if only in a small amount. This was an assumption made in the experiment. Thank you.